All right, here we go. Okay, so as we just mentioned, independent and dependent probability, your outcomes depend kind of on one another, right? So compound, who has heard the word compound? What does compound mean? Elijah, what does compound mean? What does compound mean? No? Well, okay, here, first let's write down our objective. Okay, your objective, ready?
No.
Okay, your objective, okay, to determine independent and dependent probabilities. Okay, to determine independent and dependent probabilities. Okay? Everybody got it?
No. Oh, what? Sorry.
To determine independent and dependent probabilities. Okay, so first, a compound event. Okay, how many of you guys, what is, you've heard compound probably in English class, right?
Yes.
Compound word, what is a compound word?
2 words.
Like 2 words, right?
Yeah. And the same.
They make a word, right?
Like Jackson, Jack, and Sam.
Okay, all right, 2 words. Okay, so kind of the same thing with probability. Okay, a compound event. Okay, this is independent and dependent events. All right.
Mr. Chrissy, where's the microphone so people hear you?
Right there.
Yeah.
Yeah.
So can they hear you right now?
Uh-huh. I am.
So if I shout
Okay, so
out-
compound probability, okay, or a compound event, okay, is 2 or more simple events. Okay? Now you understand simple probability of a simple event, like rolling a number cube, flipping a coin, right? Okay, that would be an example of compound events. If I roll a number cube and then I flip a coin. Okay? Make sense? All right. Now, independent probability. Okay, independent event basically means one outcome does not affect the other. Okay, now the example that I just gave you of rolling a number cube and flipping a coin. If I roll a 6 on my number cube, does that have any bearing on what I'm going to flip on that coin? None, okay? That's a great example of an independent event. Now, what about flipping a coin? If I flip a coin one time, whatever I get, if I flip a coin a second time, does that first outcome have anything to do with the second outcome?
No.
Even though they're the same event, okay, they have nothing to do with each other, right? Right? So you remember when we did the Skittles, okay?
Yeah.
Every time you drew a Skittle out, what did you do with it?
Put it back in.
You put it back in, right? Okay? So no matter what, every time you put it back in, the probability started over. Did whatever you drew, I drew a yellow Skittle, and I put it back in. Does that affect the next one?
No.
Not at all. Okay? That's an independent event. Make sense? Okay. A dependent event, well, obviously means what?
Relies on
Okay? Dependent,
the one outcome.
a dependent event, okay? One outcome
Affects the other.
does affect another.
So basically.
Okay? Now, let's say, you know what I'm going to do? Let's do this. Look. Okay, these are my cups of cubes. Okay? Let's just say this. Okay, I'm going to make it real simple. Okay? In this cup of cubes, I have a yellow, a green, a pink, a white, and an orange. How many are there?
5.
There are 5, okay? So I'm going to give you an example of a dependent event, okay? If I want to find the probability of, pick one of those colors, Jose. Okay? Probability of white, Teeter, pick another color. Okay, so if I want to find the probability of getting a white, then a pink, okay? The key word that you just heard was what? Then. That means I have to have one, then something else happens, okay? So what's the probability, okay? I drew a white, right? What's the probability of me getting white? 1 out of how many?
5.
5, because there's one white out of 5, right? Everybody agree with that?
Yeah.
Now, I took that white out. There's no more white cubes in here. Well, Teeter wanted me to get a pink on the second one, right? Is there still a pink in here?
Yeah.
There is, but the problem is what? It's no longer 1 out of 5. Why? How many cubes are there?
4.
There's 4. So did this outcome depend on that outcome?
Yeah.
It did, okay? Because I no longer have 5 cubes, I now have 4 cubes. Does that make sense? All right. Good. So let's look at, can you guys see that, or you guys can see that okay, right? Okay. Let's look at this first example. Okay? This says a coin is tossed and a number cube is rolled. Before we even do anything, okay, are these independent events? Okay, if I flip a tails, is that going to affect what I roll on a number cube?
Yes.
No.
No, not at all. Okay? There's no effect. Okay? I can flip a coin 1,000 times and it's still not going to affect what I roll on a number cube, right? Okay. So what I'm going to do on this says what? Find the probability of tossing a tails, but then I see this word, and rolling a 5. Okay? So the first thing I'm going to do, what's the probability, Sailor, of me tossing a tails?
1.5.
1 out of 2, right? This is the probability of getting tails. Tails. Now, what's the probability of rolling a 5?
1 out of 5. 1 out of 6.
How many 5s are there?
1.
1 out of how many?
6.
6. Okay? So the probability of a 5 would be 1 out of 6. Now, this thing right here, this is a very important word. Because not only do I have to flip a tails, but I also have to roll a 5. Okay, let's say that you win $100 if you roll a tail, or you flip a tails and you roll a 5. Okay? If I just flip a tails and I don't roll a 5, did I win? No. Both of those have to happen. So if I wanted to figure out the probability of that happening, I'm going to take these two fractions, and what do you think I'm going to do with them?
Add them.
I'm going to not add them, but I'm going to multiply. Okay, Chase, what's your question?
Well, is that technically dependent? Because if you roll a heads, it's like you can't roll a 5.
Well, the thing is, this outcome of a 5 wouldn't have anything to do with the heads.
Okay.
Okay? I mean, I understand where you're coming from, and that's good thinking. But what I get on that coin has no bearing on what I can get. Does that make sense? Okay? So if I multiply these, what's 1 times 1? 1. What's 2 times 6? 12. That's it. All I want you to do is write it as a ratio. Okay? Question, Brooklyn.
So couldn't everybody do that? Because it doesn't say how many times you have to roll.
This is just saying on 1.
Oh.
Okay. Do we get that one? Okay. Now, obviously, it's going to get a little more tricky, but let's go ahead and go to the next example. Okay, in your notes, if you would look at the second example, I need to make that a little bigger. Hold on just a second. Braden, you're going to have to wake up, Holmes. That's your problem. Okay. So a bag contains 7 blue. Let's pretend this is my bag. I have 7 blue, I have 3 green, and 3 red. So how many marbles are in here?
13.
13 marbles. Okay. So 13 marbles. Okay. If Agnes randomly draws 2 marbles from the bag, one after another, what is the probability of drawing a green and then a blue? Now, we got to think about this for a second, don't we? If you read it carefully, what does it say?
Then.
She's drawing 1 and then what?
After.
And then another one. Okay, so do you think this is going to be dependent probability?
Yes.
So I have 13 marbles in here. Okay? And if I want to know drawing a green, how many of these 13 are green?
13.
3. So the probability of getting a green on the first one is 3 out of 13. Does everybody understand that?
Yeah.
Now, then I have to get, ooh, there's that word, man. Then I have to get a blue. Okay, how many blues are in here?
7.
There are 7 blues, but there are no longer what? Guys, I took a green marble out. There's still 7 blues, but there's only how many marbles?
10. 10. No, there's
Okay.
10. There's 12.
12. Guys, I only took 1 green out. So it is 12, okay? Now, when I multiply these fractions, okay, I can multiply these big old numbers, but I know a trick, and I know you know a trick because I showed you the trick. What's the trick?
Cross multiply.
Cross.
Cross products.
Butterfly.
Cross butterfly. Yes, we're going to cross butterfly this.
And then that one's
Cross what? Come on.
multiplication.
No.
Cross.
Soul. Cross cancel. Okay?
And cancel.
I cannot cancel anything with 7 and 13. But does something go into both 3 and 12?
Yes.
I want 2.
3 goes into 3. Sit down, dude. 3 goes into 3 once. And 12 divided by 3 is 4. Now I'm going to multiply. 1 times 7, 7. 13 times 4,
52.
52.
Yeah.
Now, can I reduce this at all?
No.
No.
Unless you put it in a
Okay, shh, don't talk. What I want you to do, before I move on to the last example, I want you to find the probability, this is completely separate, of getting a red, then a green. Do that for me. A red and then a green. Don't sit. Do this. Come on.
I am.
Do you have to make the other one a 12 again?
I don't know. Do you?
Since you took it out?
I don't know. Do you?
Well, it doesn't say if you took it out.
I got the answer.
Well, I have a red and then a green. So did I put it back?
I got the answer.
Okay, Brooklyn. What's the probability of getting a red?
3 over 13.
3 over 13. Do you guys agree? I agree. Okay. Brooklyn, what's the probability of getting a green?
3 over 12.
3 over 12. Now, how many of you guys got that first part right? Okay, good. Now, I can do one of two things. When I cancel this, I can either cross cancel these, or I can do what? Can I reduce 3 twelfths?
Yes.
If I reduce 3 twelfths, does it change the value?
No.
Think about this. Is 4/8 the same value as 1/2? It is, right? Okay. So if I reduce this to 1/4,
It's still the same.
I'm still going to get the same answer, aren't I?
Yes.
What's 3 times 1?
3.
3. What's 13 times 4?
14.
52. Okay. Do we raise your hand if you understood what we did on that one? Okay. Now let's look at the last example. Okay. There's a couple of examples on your worksheet with cards. Okay. So before we do anything with cards, let's determine some stuff about cards. How many? We're not including jokers. How many cards are in a deck of cards? 52. How many colors are there? Or how many suits are there? There's hearts, diamonds, clubs, and spades. Right?
Yeah.
Okay. So you got to keep that in mind. Okay. All right. So if I am looking at this last example, okay, this says a standard deck of playing cards contain 52 cards and 4 suits of 13 cards each. 2 suits are red and 2 suits are black. Find each probability, then assume the first card is replaced before the second card is drawn. Okay. It didn't give us a problem, did it? Okay, let's do this. Let's say the probability of a red queen and a black 2. Black 2 of clubs. Okay, now, there is a really important word here. Okay? Actually, a really, really important 2 words. Can anybody identify the really, really important 2 words here?
Red and black.
Jose?
That's one.
Well, that is important too. But when we determine it, Teeter? Well, that's important too, but not what I'm looking for. Chase?
there's no before.
No. Trevor,
In the problem or in like?
in this part. In this part.
Oh, it says the first character put.
Bam! Oh man, it's so important. This right here.
Oh, yeah.
When you see those two words, what does that imply? Does that imply automatically? Does that tell us this is dependent or independent?
Independent.
Independent.
Yeah.
Remember the Skittles, guys. When I took a Skittle, I put it back. Right? Okay. So let's look at this one. How many red queens are there?
1.
2 out of how many? 2 out of 52. You guys agree?
Yeah.
Can I reduce that?
Yeah.
1 over
Don't know.
26. Okay? All right, that's my first probability. How many black 2 of clubs are there?
1.
1 out of how many? 52.
Oh no.
Now I'm going to multiply. 1 times 1?
1.
1.
And
26 times 52. I'm going to do that in my head real quick.
Wait, that's a calculator.
Carry my, 1,352. Aren't you impressed on how fast I do that?
oh nice.
Okay.
What the heck?
I know. It's great.
Why ain't there still?
Yes.
How did we get the 1 over the 2 again?
Okay, because there's only one black 2 of clubs. Okay?
Oh, there is?
Yes.
Oh,
I mean, there's
okay.
2 black cards, 2 black 2s. One of them is clubs, one of them is spades. There's only one black number 2 of clubs.
Is that a six?
Okay.
6?
Oh, here you go.
1 over 6?
1 over 26. Just leave it there. Okay, does this make sense?
Yeah.
Okay. I'm going to go ahead and pass out your worksheets. You may use calculators.